We have seen how a mass like our Sun can bend light. It's not hard to extend this simple concept to what a galaxy of hundreds of billions of stars could do. Galaxies have a mass distribution with the maximum at the center trailing off to a minimum at the edges. This distribution acts like a lens for light passing through it. Here's the bottom of a wine glass with a configuration similar to a galaxy. You can see what it does to the graph lines as it passes over them. When we repeat the movement over a star, we see how it distorts the light into a circular pattern. We call a bending of light through gravitational fields gravitational lensing. Here's how this lensing works on a galactic scale. A distant galaxy would be seen here on Earth directly if there were no intervening massive cluster to bend its light. But with such a cluster, the light from the distant galaxy gets bent. Light bent in our direction will continue on to Earth. Working back from the Earth's point of view, we see the distorted and magnified image. The amount of bending depends entirely on the structure of the lensing cluster. Magnifications can range from a factor of 2 to 40 times the size of the distant object. We'll see that, under the right circumstances, an object can be magnified by over 1,000 times. In the course of analyzing this Hubble image, astronomers discovered that ESO 325 is actually a gravitational lens. This means that the focusing power of the enormous mass making up the galaxy caused the light from some distant object, probably a distant dwarf galaxy, to be deflected and magnified. As a result, the more distant galaxy appears brighter and distorted into the shape of an arc or ring, known as an Einstein Ring, because the phenomenon was first predicted by Albert Einstein. Here's an image created by adding data collected by the Multi-Unit Spectrographic Explorer instrument on the European Space Observatory Very Large Telescope. This was the first test of Einstein's light-bending theory done outside of our own galaxy. It passed the test, demonstrating that the theory held across the universe and not just in the Milky Way. Here's another one. The foreground luminous red galaxy, 4.6 billion light-years away, has about 10 times the mass of the Milky Way. The blue arc around it is the gravitationally lensed image of a more distant galaxy, 10.9 billion light-years away. The object's name is the Cosmic Horseshoe. Astronomers first discovered it in 2007 using data from the Sloan Digital Sky Survey. But this Hubble image offers a much more detailed view. Although the universe is filled with galaxies, Einstein rings are a rare occurrence because it requires an almost perfect alignment of a distant galaxy with an intervening one that has enough mass to gravitationally focus the light. But a number have been found. Here are 8 of them from the Sloan Digital Sky Survey and Hubble. We've seen how massive galaxies can act as gravitational lenses to create Einstein rings. You can imagine how massive clusters with thousands of galaxies would produce much larger and more powerful gravitational lenses. But before a gravitational lens can provide accurate, detailed information about the object being lensed, we need to know its light-bending characteristics. Clusters of galaxies don't provide smooth lenses. They are quite complex, and no two are alike. The source object's light is bent by the cluster's clumpy matter distribution. And to make it harder, most of the cluster is dark matter that we can't see directly. All this makes cluster lens analysis very difficult and time-consuming. But with these magnifying glasses in space being our only window into the early universe, astronomers and astrophysicists have been analyzing galaxy cluster lensing for half a century now. We'll start with the Coma cluster to illustrate how they do it. The first step is to measure the radial velocities of every galaxy in the cluster from their Doppler shifts. This is then generalized into their three-dimensional velocity dispersion statistical equivalents. This galaxy motion gives us the kinetic energy of the cluster. This allows us to solve for the mass of the cluster. In addition, each lensed object found in the cluster is analyzed to calculate the magnitude of the mass needed to create the observed distortion. The end result is a model for what the cluster will do with the light passing through it. To illustrate the basic geometry of gravitational lensing, we'll use the giant galaxy cluster WHL0137-08's lensing of the sunrise arc. Here's the basic geometry of gravitational lensing. This is the sunrise arc light on a direct path to us, as if the galaxy cluster was not there. We could not detect this light. It is too dim for even our most powerful space telescopes. Here's its light, heading in another direction. As it encounters the cluster, it is bent towards us by the cluster's mass. We can estimate the deflection angle once we know the mass and center of mass of the cluster. On Earth, we observe the image to be on a straight line at an angle from its actual direction. The lens equation gives us these angles. This geometry enables us to map points seen on the lens plane back to its position on the source plane. Note that the magnitude of the light bending changes for objects closer to the lens. The lens magnification will decrease as the ratio of the distance from the lens to the object over the distance of the lens to the observer decreases. Here's an example. In this image, a remote galaxy has been distorted and magnified by a factor of 20 by the gravitational lensing. Lensing effects also created multiple apparitions around the curved arc of the single background magnified galaxy. The object was nicknamed the Molten Ring because of its appearance. The typical magnification created by this lensing ranges from 20 to 40 times the source size. But there is one more additional optical process involved that can magnify an object thousands of times over. Here's how it works. Picture a set of uniformly distributed particles on a line, each with slightly different velocities. They start out with a uniform particle density, but because of the small velocity differences, the particle density will vary as time goes by. Areas of high and low density will develop. The density at a later time, t, is described by an equation. The equation has hotspots when the denominator approaches zero. Expanding this to 2 dimensions, we get density peaks along curved lines that themselves intersect at points with maximum intensity. I see this phenomena in my own backyard swimming pool. Sunlight is evenly distributed as it reaches the water's surface. Small waves on the surface are creating small changes in the sunlight's direction. It's the caustic process that generates the lines at the bottom of the pool. These lines are not ripples in space-time. They are simply lines of intense light magnification. Light passing through a galaxy cluster is impacted in exactly the same way. Lines of extreme magnification, referred to as lensing critical curves, are created by the caustic process. As a distant object approaches a critical curve, its image will be duplicated side by side, and under some circumstances will develop yet a third image. Astrophysicists and astronomers model these lines and use the lens equations to map them back to their source. They can then reconstruct the shape and dimensions of an object, determine its deformation, calculate its observed magnification, and deduce its intrinsic luminosity. Here's an example. This galaxy is visible twice because its light has approached a critical curve, or sometimes referred to as a ripple of dark matter, in Abell 68. The galaxy cluster MAX 1206, 4.6 billion light-years away, has produced 47 multiple images of 12 newly identified, more distant galaxies, as seen in this Hubble picture. This dashed line identifies a calculated critical curve for a galaxy 3.2 billion light-years behind the cluster. This solid line identifies a calculated critical curve for a galaxy 8.3 billion light-years behind the cluster. You can see how the gravitational lens characteristics change with the distance to the faraway sources. We covered the Hubble constant in depth in the How Far Away Is It video book. It was developed by Edwin Hubble in the late 1920s with his studies of nearby galaxies. He used the cosmic distance ladder Cepheid variables and Type 1a supernova standard candles inside distant galaxies to determine receding velocities. His constant gives us the rate at which the universe is expanding. Today's current value from distance ladder measurements is 22.7 kilometers per second for every million light-years further away a celestial object is. In 2016, a group of astronomers used the Hubble Space Telescope and others to study 5 galaxies, gravitationally lensing 5 quasars, in order to arrive at an independent measurement of the Hubble constant. The strong gravitational lensing creates multiple images of the background quasars. Quasars are incredibly luminous galaxy cores. It is thought that they are massive black holes actively accreting huge amounts of matter. Some of these quasars flicker. While the relative time between 2 flickers is correctly represented in this animation, in reality the delays are on the range of 2 days to 2 weeks. Because the lens quasar is not perfectly aligned with the lensing galaxy, and the lensing galaxy is not perfectly spherical, the light from the different images of the background quasar follow paths which have different lengths. The delays between them depends on the lengths of the paths the light has taken. It is possible to determine the Hubble constant from the flicker delay time. Here's the lens equation we covered earlier. If we mark the length from the observer to the first flicker, and mark the length from the observer to the second flicker, we create an angle. The distance between these 2 points will be equal to the light travel time delay multiplied by the speed of light, adjusted for the redshift of the lensing galaxy. Analysis of the lens itself also gives us a measure of the distance based on the lens mass distribution geometry. It's based on an optics principle first discovered by the French mathematician Pierre Fermat in 1662. In fact, Fermat's principle holds in the general theory of relativity, where gravitational lenses replace glass. These 2 distance quantities are responsible for the measured time delay, so they are equal. You can now solve for the Hubble constant. With accurate measurements of the time delays between the multiple images, as well as computer models for the lensing galaxy, the team determined the Hubble constant. It is in agreement with the Type 1a supernova method. One of the most interesting uses of strong galaxy cluster gravitational lensing involves distant supernova. Multiple light paths through the cluster produce multiple arrival times here on Earth. Here are a few examples. In 2014, a team of astronomers found a supernova in this galaxy cluster, over 5 billion light-years away. The supernova actually happened in a galaxy 4 billion light-years beyond that, making it 9 billion light-years away. The huge mass of the foreground galaxy and galaxy cluster bent the light from the distant supernova, creating 4 separate images of the same explosion. The images are arranged around an elliptical galaxy in a formation known as an Einstein Cross. Following this discovery, astronomers modeled several possible gas and dark matter distributions in the galaxy cluster. Each model predicted that another image of this supernova will appear in the cluster, but they had different time estimates ranging from 2015 through 2025. In December 2015, it appeared. For the first time in history, the time and location of a supernova was accurately predicted. We actually saw the supernova happen. Instead of detecting a flash in the sky and turning telescopes to its location, we had the telescopes already focused on the correct area and recorded the event from beginning to end. This also constitutes a measure of the speed of light without the use of mirrors. Here's another one. 3 views of the same supernova appear in this 2016 image on the left, taken by the Hubble Space Telescope. But they're gone in the 2019 image. The distant supernova named Requiem is embedded in a giant galaxy cluster 4 billion light-years away. The cluster gravitationally lends the light from the supernova located in a galaxy far behind it, 10 billion light-years away. It also split the supernova's light into multiple mirror images, highlighted by the white circles in the 2016 image. Based on the foreground galaxy's dark matter distribution, researchers predict that a reappearance of the same supernova will happen in 2037. The predicted location of that 4th image is highlighted by the yellow circle at the top left. And like we did with flickering quasars, time-delayed supernova images can also be used to calculate the Hubble constant. In 2017, a Swedish-led team of astronomers used the Hubble Space Telescope to analyze multiple images of a gravitationally lensed Type 1a supernova. This had never been done before. Here we see the lensed galaxy in the middle frame. It's over 2 billion light-years away. The 4 images of the supernova can be seen in the rightmost frame. It originated over 4 billion light-years away. These 4 images of the exploding star and the time difference in their light profiles can be used to measure the Hubble constant in a completely different way. Since the light travel times for the various images are unequal, intrinsic variations in the source would be observed at different times in the images. The time delay between images is proportional to the difference in the light path lengths through the lensing galaxy's spacetime, which in turn is proportional to 1 over a Hubble constant. So by measuring redshifts and time delays, and by producing an accurate model for the lensing galaxy, the Hubble constant can be calculated. Distant giant galaxy clusters, around 4 billion light-years away, have been able to lens galaxies twice that far away. Without gravitational lensing, we would never have detected these more distant galaxies. At these distances, we need to take into account the expansion of the universe in order to determine how far away they are. For that, we use the Friedmann metric. With this, and a stated set of coefficients for the flat lambda cold dark matter model, we get the galaxy's distance from us when the light we see started its journey, the distance the light traveled to get here, and the distance from us the object is now. Here are a few examples. Astronomer Timothy Hamilton, using the Hubble Space Telescope, discovered these unusual objects now named after him. The objects are the stretched images of a gravitationally lensed distant galaxy, located more than 7 billion light-years away. One appears to be a mirror image. In this case, a precise alignment between the background galaxy and a foreground galaxy cluster 7 billion light-years away produced twin magnified copies of the same image of the remote galaxy. This rare phenomenon occurs because the background galaxy straddles a ripple of dark matter in the foreground galaxy. As the faraway galaxy light passes through the cluster along this ripple, two mirror images are produced, along with a third image that can be seen off to the side. This Hubble image shows a massive galaxy cluster about 4.6 billion light-years away. Along its border, 4 bright arcs are visible. These are copies of the same distant galaxy, nicknamed the Starburst Arc. It's almost 11 billion light-years away. Its light is being lensed into multiple images by strong gravitational lensing. The Starburst Arc is among the brightest lensed galaxies known, and its image is visible at least 12 times within the 4 arcs. Here's a closer look at 3 of them. The lens makes various images from 10 to 30 times brighter. This allows Hubble to view structures as small as 520 light-years across, a rare detailed observation for an object that far away. This is a close-up look at the brightest distant magnified galaxy in the universe known to date. It is one of the most striking examples of gravitational lensing. In this image, the light from a distant galaxy, nearly 10 billion light-years away, has been warped into a nearly 90-degree arc of light in the galaxy cluster. The galaxy cluster that is bending the light lies 5 billion light-years away. Here's another one. The light from this galaxy traveled 4.48 billion light-years to get here. These foreground galaxy clusters are magnifying the light from the faint galaxies that lie far behind it. The faint light from these lensed galaxies traveled up to 12.8 billion light-years. It's the gravitational lensing that allows us to see that far back in time. Without the magnification, these galaxies would be invisible for us. This is Abell 1689. It's one of the most massive galaxy clusters known. The gravity of its trillion stars plus dark matter acts like a 2 million light-year wide lens in space. Here's gravitationally lensed galaxy A1689-ZD1. It is one of the most distant spectroscopically confirmed sources, with a redshift of 7.5. We are seeing what ZD1 looked like when the universe was only 700 million years old. It is the earliest known galaxy where dust was detected in its interstellar medium. And surprisingly, it has the same ratio of dust to total mass as very mature galaxies, such as our own Milky Way. Gravitational lensing of objects on or near critical caustic curves can actually identify individual stars in a lensed galaxy. This is referred to as microlensing. To illustrate this ability, we'll cover 2 examples, Icarus and Earendel. Here's MAX J1149, a foreground galaxy cluster 5 billion light-years away. We used this lens when we covered the Refsdal supernova. Here we lensed the single star nicknamed Icarus in a galaxy 9 billion light-years away. In 2018, this star was astride a critical curve. It was magnified around 2,000 times its actual size. At that time, it was the furthest individual star ever seen. The colors of the light coming from this object showed that it was a blue supergiant star. This type of star is much larger, more massive, hotter, and possibly hundreds of thousands of times intrinsically brighter than our Sun. By 2022, the star had moved off the critical curve and is no longer visible. Here we have a massive galaxy cluster. It has been studied for over 5 years, since Hubble first captured the image in 2016. The galaxy was 4.5 billion light years away from us when the light we see started its journey. The light traveled 5.6 billion light years to get here, and it's currently 7 billion light years away. In this cluster, Hubble discovered a gravitationally lensed galaxy, nicknamed the Sunrise Arc. Its redshift is 6.2, with an angular size on the sky exceeding 15 arc seconds. At that distance, this makes it 410,000 light years long. The galaxy was only 3.9 billion light years away from the Milky Way when the light we see started its journey. The light traveled 12.9 billion light years to get here, and it is currently 28 billion light years away, receding faster than the speed of light and beyond the visible horizon. No light leaving that galaxy now will ever reach the Milky Way. In this galaxy, Hubble discovered a single star. The star, LSZ6, is nicknamed Earendel. The light we see from this star began its journey 900 million years into the universe's expansion. This makes it the oldest, most distant individual star ever seen. In addition, it is at least 50 times the mass of our Sun and hundreds of thousands of times brighter. This makes it one of the most massive stars known. Stars that massive only last for a few million years, so Earendel is long gone, having spewed the heavier elements it created into ZD1 to become part of the next generation stars. On July 30th, 2022, a few months after Hubble's discovery, a team of astronomers called Cosmic Spring worked with Webb to train its near-infrared imaging camera on the Sunrise Arc for over 4 hours as part of a survey of the galaxy cluster. It also managed to capture the red dot corresponding to Earendel. Webb's analysis of the image has already confirmed that this is indeed a single star system and not a group of several stars. The red dots on either side of Earendel are a single mirrored star cluster. Here's a higher resolution image of the area around Earendel produced by the James Webb team. Objects close to a critical curve get mirrored into multiple images, like these two images of a star cluster inside the Sunrise Arc galaxy. The critical curve responsible for this will pass through the midpoint of the two images. An object found at this midpoint, like Earendel, would be so close to the critical curve that its multiple images cannot be resolved. It will appear as a single object. 4 different models were used to locate the lensing critical curves. Here's one of them. The others are quite different, but they all pass through Earendel. The magnification drops off rapidly as the distance from the line increases. Earendel's distance from the line is within 0.1 arc seconds. That's a very small angle, but at these distances, it represents 2,730 light years. This distance, along with its shape, puts its magnification between 1 and 40,000, with 9,000 being the most likely. With this, and the size of the image, we get a source object that has a radius less than 617 billion kilometers. That's 383 billion miles. This is 100 times smaller than known small star clusters, leading to the conclusion that it is a single gigantic star or binary star system. Now that we can examine stars this far away with gravitational lensing and the James Webb Space Telescope, I'm hoping that we will even get to the point where light fluctuations from a star like Earendel will someday tell us something about the earliest planets.